Okay, guys, welcome to another episode of CUDA Education. Today is going to be a long one, so I need your guys' attention. Um, what we're attempting to do is basically change the way how the application runs. This is the compute ray tracing application. So we're changing the application so that instead of using the sampler, the texture sampler, we are going to do a direct image load. And this is all following up from the previous conversation. In the series, you could look in the labeling of the video to see what series it is and what you know what part of the series that we are currently in. But the first video was investigating the texture sampler approach, where basically you have an image, but then you do some texture sampling, you do some extra processing to make the final image what you want it to be. Um, let me run the application just so we have some context. Right. So we have this application here. I'm running it on my integrated graphics card because I kind of want it to be slow, and so we could actually just get closer to what's actually happening, and just the struggle that the integrated graphics card has. If I run it on the Nvidia card, it will run a lot smoother and better frame rate, and it would just be better. But for our intents and purposes, this is not, we're trying to learn stuff and whatever. So it just, I'd rather run it this way. Anyway, so you see these shiny sort of the nice processing of the image and everything. That is as a result of the texture sampling approach, where you have a written image that's drawn via compute, but then you do some massaging of that image to basically improve it and make it better looking and all that stuff. But what we want to do is we want to circumvent this approach. We want to basically just load whatever is computationally created as the image. We just want to load that image directly to the screen. So what is supposed to happen is that um, what is the raw direct image is going to be less appealing. It's going to be less finessed and appealing as what we have now. And in order to actually get this done, I'm going to rely on my trusty assistant that was recently created. It's a very brilliant assistant. Like, literally, this assistant is the greatest assistant uh, that you could ever find, and that assistant is, of course, ChatGPT. Okay, so um, we're gonna ask ChatGPT to basically help us to take out the sampling texture sampling thing and just load the image directly. Now, the thing about it is that in the sort of, there are two components. There's a main source file, the .cpp file. That's this guy right here. So we could see that we have the .cpp file, which is sort of CPU side, that's writing the instructions, and has your we're editing in Visual Studio and stuff. But then we also have the texture.frag file, which is up here, which deals with the CPU side. So this is our shader. This is our shader. So these are the shaders here, right? These are the shaders. We're dealing with GLSL. These are the shaders, and we do have our source file, which is CPU side, but it's writing our instructions for what we want done and all of that stuff. But then we have our shaders, which is on the GPU side, that actually takes the sampler and then basically uses this texture function to output what we want, right? So right now I have this one running, which is the default application, um, the default application. But then I also as a ways of just seeing what's happening, I commented this out and I ran this one just to see the change in the output. Okay, but this texture function is what sort of is being used to help us massage the image to get it to what we want, right? And that of course has the sampler color thing here, which is binding 0, and that is related to, so we have our vk lowercase vk create sampler blah blah blah, and then we do have uh, we do have the binding that basically moves it over to where is it? I guess it's this guy, right? So if we go to create, go to definition, right, the binding is 0. So I'm going to assume it's this guy. The previous episode goes into more detail with it, but this guy right here basically transfers over to here. We have our sampler color here thing, and that is after, this is inputted after we have processed um, all of this guy right here, and then we run our texture function here that basically outputs to the screen. Okay, but we're doing a lot of massaging. Okay, so the previous episode in the series will we play around with this stuff and we get into more detail, right? But I don't want to get bogged down in the previous stuff. I want to move on ahead. Okay, so the idea is that we're going to ask our friend ChatGPT to basically help us to basically make the transition, right? So right to replace right the right. So I'm mapping the smallest set of changes needed to replace sampled texture presentation with direct storage image reads. So I can give you a clean rename and blah, blah, blah. So yes, the direct way you want is usually called storage image access or image load store/store. And in the shader, the read side is typically called image load access, right? So instead of this texture function that we use, we are going, instead of the texture function that we use here, right? We're just going to do a direct image load. So yes, the direct way you want is usually called image storage image access or image load/store. And in the shader, the read side is typically called image load access. In this sample today, the graphics pass is set up as a combined image sampler at binding 0, right? Which is what we talked about. And the fragment shader reads it with the texture function. The app then draws a full screen triangle to represent the compute result. Okay, so we follow that, right? Because the app then draws the full screen. So the comparison is current path is texture sampling combined image sampler, right? So this is the correct nomenclature for what is currently happening. Is you could either call it texture sampling or combined image sampler, but we want the direct path, which is a storage image access slash image load function. So basically we're not going to call this texture function, we're going to call image load, the image load function. The direct path is less appealing visually because image load gives you exact texel values with no filtering and no sampler behavior like clamp, repeat, border, color, etc. That is exactly the raw look you said you want. The storage image already exists because the compute shader writes the ray traced result into it. So you are mostly changing how the graphics part pass reads it and not how the compute pass produces it. The storage image already exists because the compute shader writes the ray traced result into it. So you are mostly changing how the graphics pass reads it. So this is important, how the graphics pass reads it, not how the not how the not how the compute pass produces it. So in other words, the compute pass is already creating the image, right? It's already giving you a result. It's just that when you now go through the graphics pass, you are massaging it with, all of this sampler stuff, right? And changing it up and making it nice and smooth and stuff and all the things that we want, right? Including, how do you display the full image? Do you just put the image in a corner of the screen? All of that stuff, right? So really what we have to do is we have to change how the graphics pass reads it and not how the compute pass produced it, because the compute pass is producing its raw image as it always has, whether we're talking about what we're currently doing or what we're going to do, in our new modification. So what to change? Change the graphics descriptor from combined image sampler to storage image. Right now, prepare graphics declares binding 0 like this, right? So and write storage image descriptor into that slot as a combined image sampler, right? So basically, if I just copy this, right? So if I go here, I don't think it's so. So we have initializers, descriptor set layout binding, blah blah blah, and right. So as we said, the graphics pipeline uses one set and one binding. Binding 0 storage image with ray traced output as a sampled image for displaying it. So this is where we set up, we basically communicate from our source file over to our shader file, you know, this guy, sampler color, right? So that's this guy that it's talking about here, right? This is under prepare graphics. So we're under prepare graphics, this portion right here. So right now, prepare graphics declares binding 0 like this, blah. And notice that we have our 0 right here, right? Because when we looked at the definition, so go to definition, right? We have the binding as 0, and then this is hard coded. Descriptor count is hard coded as 1. So we don't actually call this, in our file, because it's already hard coded in. So we just put this in, and then it takes it and whatever. Okay, so and write storage image descriptor into that slot as a combined image sampler, right? Change that binding to, so we're going to change it now to, instead of combined image sampler, we're just going to do VK descriptor type storage image um, for that piece, and change the descriptor write to a storage image write instead of a combined image write. Um, right, so let us just do this part first. So type storage image, right? So instead of it being combined image sampler, we're just going to do type storage image, right? Storage image. Okay, and we don't get any errors. Okay, so we have now type storage image, and change the descriptor write to type storage image, and change the descriptor write to a storage image write instead of a combined image sampler write. So that's gonna be image layout. Yeah, let's clean up sort of. So 298. All right, so this prepare graphics is in 298, right? Line 298. Let us see. Um, all right, so I'm looking at 213 as the. Okay, I just need to make sure. All right. I don't want to just change stuff willy nilly. Okay, so let us anchor ourselves. So we have our prepare graphics function, right? We have our prepare graphics function, right? And in the prepare graphics function, we change the descriptor set layout binding to storage VK descriptor type storage image, right? We understand that. It is in the prepare graphics function, but then the actual write is around here, and that is inside of the prepare storage image that is used to store the compute shader ray tracing output. Okay, makes sense, right? So obviously if we're writing stuff, we're doing it inside of the prepare storage image, right? So that makes sense. um, I just want to make sure. I want to search for this. All right, that is not. Okay, I think it's just storage image. All right. Don't worry about it. Let's not worry about that. Okay, so image layout is going to be storage. All right, so the image layout is the same, I believe. The view is the same, but the sampler, the storage image descriptor sampler is going to be VK null handle, right? So instead of storage image sampler, go to definition. No, we don't care about that. Okay, we're just going to change this to VK null handle. So VK underscore null underscore handle. Okay, so VK underscore null underscore handle. Okay, so we're now taking out the sampler. Um, okay, let's see. Okay, so write descriptor sets. We are now at line 305. Write descriptor sets. Um, and we're changing now the. So let us just go to definition. So we have destination set type binding image info descriptor count. So type, I think it's type that we're right. So we're changing type from combined image sampler to storage image, right? Okay. And then 0, and then everything else should remain the same. Yeah. And then a VK update descriptor sets, lowercase VK, guys. You guys know anytime there's a lowercase VK function, we know it's important. So we're updating the descriptor set now. Um, does anything change here? I don't believe anything changes. No, nothing changes there. That matches the fact that the image is already being treated as a storage image elsewhere in the sample. The synchronization before drawing already uses a compute write to fragment read barrier on the same image in VK image layout general. So that part is conceptually aligned with the change. I am this VK image layout general. I am a little curious though as to what's going on. Okay, so um, we'll just leave that for now. Okay, change the fragment shader from sampler 2D plus texture function to image 2D plus image load. The current fragment shader uses a uniform sampler and texture function. Replace that with a storage image. So I don't know what this is all about. I probably didn't give it the official, or maybe I did, but all right, it's all right. We could figure this out, guys. So on the texture thingamajig, on the um, texture.frag shader. So again, guys, just so you follow, we are now in the texture.frag file right here, GLSL shaders, GLSL texture.frag. So we're on the GPU now, right? We're on the GPU, and it says change the fragment shader from 2D sampler 2D plus texture to image 2D plus image load. So let's just do that. So we're just gonna do image 2D, and we're gonna do um, I'm just gonna go out on a whim and say I'm just gonna change this to image load because I don't think it has my shader file fully. So I'm just gonna change this to image load, okay? And I gotta recompile the file. Remember, guys, it's an external thing. We have to recompile to spare V format. So I'm gonna do that. I do have an error. Um, okay, let me. Okay, guys. So my simplified hack didn't work. Okay, so I reverted back to the original file, and basically I just commented out, what we had here, and I commented out what we had here, right? So that was the original file was this guy here, and this guy here, and then yeah, and then that was it. You could rewind the video to see what the original file was, but my simplified thing of just changing this to image load and stuff, obviously, I mean image 2D didn't work, and changing this to image load didn't work. Okay, so Guilty as charged, but that's all right. So what actually happened is that now instead of this line right here, we have this line right here. So layout binding 0, RGBA 8, uniform read only image 2D storage image. Okay, so we have now a storage image thing here that basically we call our thing this storage image, and then we massage this storage image thing in order to get to image load here, which is what we output frag color. Okay. um, I have saved this file and I've compiled it into SPARE-V format. So, you have to compile shaders and all that stuff to SPARE-V format because uh, that .spv file, so 306. Okay, so that SPV file is what texture.frag.spv. That SPV file is what is actually read when we're loading in the shader stages, right? So, a long time coming, guys. I've been I've been at this thing for such a long time that I'm just kind of amazed at how far I've reached. But I'm not gonna leave you guys behind if you're just new. If you're new to the party, I'm not gonna leave you guys. So really quickly, what happens is that we have our source file, which is a CPU side. It's a CPU side set of instructions, right? and and we have our CPU side source file. So Visual Studio, all these instructions you're typing in on the file is CPU side. Okay. Um, but we have a thing in computer graphics called shaders, which shaders are GPU side. So literally, when you're messing around when you're messing around with shaders, you're actually writing instructions on the GPU side. And long story short, it's where a lot of the innovations in computer graphics happen. They happen on the GPU side. Okay, they don't necessarily happen, with the instructions that are made on the CPU side, aka Vulkan, right? Because Vulkan is sort of the foundation of the skyscraper. But if you want to do some whiz bang stuff and have a fireworks show and make your building the tallest it is in the city and all this other stuff, um, you could do that at the very top. But the foundation of the skyscraper has to be stable, consistent, reliable, all of that stuff, right? So that's the way I think of it. And notice here that on the shaders, which again is GPU side processing, you have competing formats. So by default, this language, I mean, these applications use the um, GLSL shader languages. So that's what we're running with. But you also have HLSL, which I believe is a Microsoft thing, and then you have Slang, which I believe is the new kids on the block that actually are trying to push the frontiers of computer graphics and everything. Actually, the neural shaders and stuff I think is I mean, ray tracing was everybody, but like the neural shaders and like AI related, injecting AI into computer graphics, a lot of it is being done on the Slang side. But that's last time I checked. Things are changing by the day, literally. But anyway, so in order for us to actually have our instructions on the GPU be updated to the new things that we're doing here, we have to compile our shader GLSL code into a SPARE-V format .spv SPARE-V format SPIR-V, that basically is like machine language. It's and the purpose of that is because for every GPU vendor, so Nvidia, AMD, Intel, maybe an ARM device, maybe an Android device, maybe some other device out there, you want to have consistent behavior with your GPU code. And that's why the SPARE-V format was created. It's created by this Kronos group, which also makes Vulkan, and they also make OpenGL and blah blah blah. But this SPARE-V format is literally it was created to keep consistent behavior across GPU vendors, because it was a big problem in the OpenGL days where a company would ship their AAA game to the world, to the market, to the masses, but based because people had different GPUs, even different GPUs in this, same GPU vendor, but different models in the whatever, you would get different behavior, you would get crashes, all that stuff. So this SPARE-V format thing is to help to make consistent behavior across all GPU vendors. Anyway, so right, so when we update the code on the shader side, we have to recompile into the we use Python. There's a Python thing, and you recompile the updates into that file, into this file here, the SPARE-V format, so that we could actually read it. The GPU could read the new instructions. Okay. So yeah. So basically, I recompiled this thing, and I was able to successfully compile it with no errors. SPARE-V didn't come back with any kind of errors or stuff like that. So we are good to go with that. And we could see that on the literally, that's what I did. So I had my old code. I basically gave ChatGPT my old code. Notice that I just changed image 2D here, and I just changed this to image load from texture, right? And then it said, yeah, there's a problem, and I checked the Chronos group. Remember, Chronos group is what makes the SPARE-V format, and it said, oh, there's a bunch of problems, blah blah blah. Right, it's basically calling me out on my errors, my deviant ways, and so it said, okay, update this line, which I did, and then put all this stuff here so that we could successfully run image load function with the coordinates and stuff, right? I don't want to get into the particulars of this right now because we have bigger fish to fry, today, but maybe in a future video. Or if you guys listen, there's homework, okay? CUDA Education assigns homework to you guys, okay? This is not just, you're going to sit down in your easy chair and just watch my videos. You actually have to do stuff, okay, on your own. So if you guys want to do some work on this, and then add some comments below the video, I would really appreciate it. But I don't want to get bogged down in this stuff right now. What I do want to do, though, is try and run this thing. So basically, if I had followed the instructions properly, um, right, so I was supposed to update this thing, but I wanted to be lazy and just like change a couple things, but that didn't work. But assuming now that we have everything the way it is, this is the direct read path, no sampler, no filtering, just exact pixel fetches, right? So we're change the fragment shader from sampler 2D plus texture to image 2D plus image load, right? Which basically is what we have down here. Image 2D and image load, okay? So that's what that was. To image, right? So replace that with that. That is the rect path rebuild. So right, it's telling me now I got to rebuild texture.frag.spv to a SPARE-V format, right? Which again, you guys know we have to get to SPARE-V format because that is the instructions that our application reads, and the GPU reads SPARE-V stuff. The graphics pipeline notes compute ray tracing texture.frag.spv. So after editing GLSL, you need to recompile that shader binary. The C++ side will not see your GLSL edits until the SPARE-V is rebuilt, right? So exactly what I said before. The C++ side, which is this guy right here, it won't see it until I recompile to the SPARE-V format. Okay. I will also say that I'm using a slightly modified function for the um, compile shaders.py function. Don't worry, because like the default one that came with the application, for some reason, for some of the applications that I was running, because remember there's a whole bunch of applications, there was like certain problems with it, and maybe the compiler that you have for this one I think it will run fine, but for some of them it wasn't. So I had to ask you know, Chat GPT and stuff to give me a new compiler. But I digress. All right. So we have rebuilt the spare V file. Optionally remove sampler creation and sampler cleanup. I don't want to do that right now. What I do want to do now is run this thing and see if it actually works. Okay, now I pray to God that I don't lose this video because I'm 35 minutes into this video and I would be really upset if I lose the video. I don't think I will, but let's both cross our fingers and see what happens. All right. So we're gonna now, we don't really have any errors. I've recompiled everything. Let us just see if we get something different. We want to see something raw and like unrefined. Well, it actually runs. It actually runs. But do we necessarily see anything that much different? I don't know. I do see that the edges of the spheres are a little bit more jagged. Um, but that's about it. Um, yeah, even this is a little bit more thing. We don't see an increase in frame rate, right? We would assume that with less processing and stuff, we would see it is a little less refined. Let's see what this image cleanup this in the current sample creates a VCAT and stores it in the. If you fully switch to a storage image president, that sampler is no longer needed for the graphics bus. You can leave it in temporarily while testing, but once the new path works, you can remove sampler creation and stop populating the sampler field for presentation. What will look different? With image load, scaling becomes nearest raw, not filtered. Sampler settings like order stop mattering for the present. The result will look more pixelated or harsher when the window size and storage image do not map one to one. That is why it is a good way. That is why this is a good way to get the less appealing look on purpose. Um, all right, so let's just run this thing again, and uh, still getting about 30 frames per second. Um, yeah, I just see the more. I was hoping to see a more drastic change. But no, we weren't that lucky. Yeah, so yeah, all right. We don't care about the before and after patch. All right, so let us just play around with this. So I'm gonna undo everything back to what it was before, right? So we're gonna do undo, 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 right? And we're gonna do undo, 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 right? Back to what it was before. I gotta recompile the shader, right? So we recompile it to the thing. And then now let's run it again and see. So this is like the clean image sampler version. We see that the a little less jagged. Um, yeah, we see that there's a little better shine on the thing, a little bit more cleaner. Um, you know, when the light goes on the spheres, it kind of does it a little bit better, right? And you could see that the outline here is a little bit cleaner, and even in the shadows, the outline is a little bit cleaner. Let us put things back. Let's do the raw image now, right? Let's go back to the raw image, and then let us see if we see anything different, right? So now we're back to the raw image. Um, oh no 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 no, we're not. Sorry guys, sorry. We got to recompile. We got to recompile. Don't let me forget. We got to recompile, right? So now, right, you could see where it's more jagged, right? It's more jagged, and then even when the light is on the spheres, it doesn't glow as nicely. Okay, it doesn't glow as nicely, but we definitely see more of a jagged edge on the shadow and on the sphere, right? We definitely see a more jagged edge. That's really all I could tell. We're still at we're still and when we compress it further, we see it even more. We're still at about 30 frames per second. Um, okay, 2930. Okay, so we're at 2930 for this guy. Even when I expand it, it's okay, we're at 27 when we expand it. Okay, so let's do another cycle. So we're gonna do undo. So we're gonna undo here, and we're gonna undo here, right? And then we're gonna recompile the shader, right? And then when we run it, we get back um, this guy, and we definitely see we're at uh, 31. I don't know, maybe um, yeah, we definitely see it's cleaner, right? We definitely see it's cleaner. And the glow on the glow on the spheres is a little bit more appealing, right? So um, yeah, it's definitely. So anyway, that's that's the episode, guys. That's the episode. I'm gonna leave it back to the original, of course. I'm not gonna go to. I'm not gonna go to. I'm not gonna go to. Wait a minute. It's definitely cleaner. And then yeah, I do see when the light goes on the sphere, I do see it being a little bit more illustrious. Okay. But all right, guys. Code education. Again, this example doesn't require you to have ray tracing hardware on your GPU. So as long as you could run Vulkan, you should be able to run this example. Um, this is the compute ray tracing example for the ray tracing examples here. You do need RTX, cards for NVIDIA and ray tracing hardware. But for this one here, you do not need ray tracing hardware. And this is Code Education, guys. Support the channel. You know the deal. If you know anyone that's artistically inclined, this is the stuff they need to be dabbling in. We're at about 45 minutes, close to 45 minutes, so I think it's a good stopping point. And yeah, guys, so we have a little bit better understanding of what's going on. We know that there's a sampler 2D and an image 2D variant and all of that stuff. Um, and we have to do processing to make sure the two gel well together. Yeah, that's it, guys. Thank you for watching. Have a great day.